Now let's look at the electric field. Electric field, okay. Because we're looking at electrostatic force. Then we'll look at the current, electricity. Okay. Then we have direct, and then we have alternating current. Okay. So electrostatic force, let's say we have this charge here, it's positive. The force is stagnant, it's not moving. So to have electric field around it, have electric field around it. Okay, to have electric field around it. Okay, that would be electrostatic force. Sometimes if you comb your hair, and as you do that, you slip or sort of get off electrons from surfaces. So you have charge bodies, okay, and those charges stay on the surface, so you have charge bodies. So you can comb your hair, okay, and then use it to attract a piece of paper which also has electrostatic force on its surface, okay, so they will attract. Okay. Now we have special generators, electrostatic kind of generators, okay. They generate charges on the surface, like the Van de Graaff generator. So like the Van de Graaff generator, okay. So this one, electrostatic force is used, okay. So either we have protons bombarding and then creating charges, and the charges are constantly earth, okay. They are earth, so that a charge stays on the body. Now what happens is if you have the electrode, the plate, okay, if there's positive, they will repel and open up, okay. If there's no charge, it closes down, right. When you are able to charge, let's say you have this surface, it's not charged, you bring a charge body, negative, here, it will repel the electrons here, the electrons here will go, so the electrons will come here. Once they have moved here, this becomes positive, okay, electrostatic, this becomes positive. So this is induction. Induction means you bring them close, but they don't touch. Induction, okay, charging by induction. Now if you want a positive charge, you connect this one to earth, okay, or you allow the current to go into the earth, okay. The earth is a good taker of electrons and also a good giver of electrons, okay. That's the deposit, the earth, okay. So if you put it connected here, once this stays in contact, this will go away and then the whole thing becomes positively charged, okay. So that's one way of generating producing charged electrons, charged bodies, okay. So this becomes charged body. The same way you can do the reverse. If you bring a positive one here, this side becomes negative, okay. Right, once this stays in contact, if you connect, then you are able to have a negative charge. Right. So these same principles are applied in the Van de Graaff generator, but these ones are able to build up very high charges, okay. Right. Good. So that is the point. So another same electrostatic force. If you have a sphere and the surface is positive, it's positive. It's positive. Okay. The inner part will be zero. Why? If let's say this side is negative, this is negative, this is negative, this is negative. This force is this way. This one is also coming that way, so they will cancel out. Okay. That's sort of opposite forces. Okay. They are equal, so they cancel out. So at the net inside here is zero. Okay. And this was Faraday's discovery. Okay. So they can have what you call the so if you wish to protect somebody, you can let them be in the Faraday, what you sort of sometimes call Faraday's cage, okay? Because if you are inside here, you are protected from charges, okay? There's no charge there. Or instrument, you can put instrument in there to protect instrument, okay? So this kind of principle has been used, okay? That the core of the sphere, the center will be zero, the charge there will be zero. as I've demonstrated from the institutions. Right, so we move on. Now let's look at some few calculations. So we've already said by the definitions, another thing that we went on, said force is proportional to the product of the charges. So let's say I have this body, I have another body here, they are separated by R. Okay, so according to the same principle like Newton said, the force will be proportional to the product of the, so this one charge, product of the charges. That same force is also proportional to the inverse of the distance squared. So F is equal to, if you put the two together, going to get F is equal to K. K is the constant of proportionality. Or let me first go this way. It becomes proportional to Q over R squared. Now let's remove this proportionality and put, once you put equal sign there, you must add your constant of proportionality. So Q over R squared. Now this Q has been found out to be equal to 1 over 4 pi epsilon naught. This is permittivity of the space, okay? Of course, when it's zero, it means it's vacuum we are talking about, okay? Vacuum we are talking about. Right, so that is it. Right, so if you put that in the equation, then you're going to get Q 4 pi epsilon naught R squared. This is the force. Now let's look at let's try to build up from the force. We know that the intensity, the electric field intensity, which is denoted by E, will be equal to your force over your charge. Okay, so if I have this charge here, this is the charge of reference. Okay, if I want the electric field intensity here, is the force here divided by unit charge, the charge that we put there, divided by the unit charge. Okay, right, so the charge that we put there will be the unit charge there. Okay, right, so that is qualifying the force per charge here. So the force is given by Q R squared here, and I'm dividing this by Q. Okay, so this Q will cancel that, and I'm going to get what? Q R squared as my E. Okay, so that will be my E. Right, so from here, you can go on. Now, if we want, if it is a surface, it is a sphere, okay, 4 pi R squared. 4 pi R squared, the surface area, okay, if it's a surface. Now, this is E here, that's E here. So, if you want the total E, then it's the sphere surface, we should multiply E by the surface. So, total E will be equal to what? E, or total what? Force, the total intensity over the sphere, total intensity over the sphere will be this E times the area. E times the area, okay? That will give us the total intensity, okay? The total intensity over the surface. Okay, when you divide force by Q, you are getting the intensity for this area. And that is per charge there, okay? Good. So if you want the total, you multiply by the surface area, multiply by the surface area, and you are getting the total. Because if this is a sphere, you have various points, all having F over Q. Right. Okay. Some also denote it. So we're going to have E, the total. That's the total what? Intensity. Total intensity will be E times A. Okay, and then you know E is equal to, from here, E is equal to K over Q R squared. And surface area of a sphere, 4 pi R squared. Okay, so let's put in values and see what happens. This is 1 over 4 pi epsilon. So R squared here, or Q here. This is 4 pi R squared here. So this cancels that. Okay. This cancels this cancels that. Okay, this is half, so this one. So we're going to have E times A equal to what? Q over epsilon naught. This is the expression we have. Now this expression is also known as the flux. It's the flux, okay? Lines of forces, okay? So it's telling us the lines of forces in space, in vacuum. The lines of forces in vacuum is flux. So that is it. So let's note this. So we can go through the equation to arrive at this as the first point that you can look at or meet. Right. So force per unit charge is intensity. It gives you the unit force per area. So if you want the total intensity over the surface, then you multiply by area. Okay, if you multiply by the total area, it gives you the total intensity. So, right. So based on that, I think up to this point, that's okay. So the formulas, you can remember them and then use them in your calculations. Now let's look at this. Let's assume this is a positive charge. Okay, it has force around it. Now this is point A and this is point E. And then we have a unit positive charge here. Now we are moving this to this point. Okay, we want to find the work done. We are moving this to this point. We want to find the work done. Now to find the work done, we know work done is equal to force times distance. Okay, right. Now the force that is in operation here, if you are moving this here, there's repulsion. The force that is in operation here is the force between the two bodies. Okay, so the force between the two bodies, that force is given by what? Q over 4 pi epsilon naught r squared. This is the force, right? Is the force that will be between them. Okay, so that's the constant force that you are moving. Okay, it depends. Then the force that is operating. Okay, within this between the two, that's the force. Okay, between the two, that's the force. Now let's see, as it moves, it's going to go through a certain distance. Let's say here, from here to that point. So the work done is going to be what this there's work done, there's any work done here, there's work done there. So this work done is going to be the force times what? The distance, change in distance. Okay, so let me make it d, something like that. Okay, right. So you can also make it the distance, since we are using distance here as r, let's use r. That will be it. Okay, and then this will be change in work. Okay, the change in work done. Okay, so this will be the force times or the distance. Actual work done is force times distance. So change in r as distance. If you are looking at change in r, the distance in terms of space, then this becomes change in work. Okay, right. So in this case, what are we going to get? We are saying that this is a unit charge 1, so it is going to this is going to be 1. So that change in work done is equal to Q over 4 pi epsilon naught r squared, okay, times our change in r. Right, so what you can do is, if you want to find the actual, the sum of, if we sum, we integrate this, we get the actual work W. So if we integrate this side and integrate that side, this is going to give us work done, which is W. And then this is going to give us what? Integration of that. That is going to give us what? Q 4 pi epsilon naught r squared the r. Okay, so this is the formula that we have here. Right, so we integrate this one with respect to the distance. The distance, let's say distance is from A to B. Okay, so in that case, you first have to integrate this one. What you have is this is constant, these are constant, so it's r. It's more or less like a constant like this over r squared, which is the same as k r negative 2. So if you are integrating something like that, all you need to do is you add 1 to it. It's going to be what k minus 2 plus 1 This is going to be minus 1, so it's going to be minus 1 divided by minus 1, okay? Right, so at the end, we're going to have what k r minus 1 as our answer. This is going to be our answer, which can be rewritten as what? K over r negative. Okay, so in that case, we're going to have what? The answer as, this whole thing is a constant. Okay, so we're going to have the answer as this. Then we are integrating from our a to b. Okay, so that so if you put in the first one, look at this over a minus, okay, going to be minus again, minus k over b. Okay, so that's at the end. I'm putting k for all these constants so that it will make it simple for us. Let's do this. So at the end, we're going to have what? At the end, this is going to give us a picture of what? Minus k over a plus 1 over b, which is the same as what? K over b minus 1 over a, k over a. Okay, so this is something like that. So that's what we're going to have. So from here, the equation is going to be this is going to be minus k over b, sorry, plus k, and this going to be minus over k over b. Okay, which is the same as k out, 1 over b minus 1 over b, right? Good. So, did we get that? Let's work it out and see. But we get the same thing here. We put in a here. So the first one will be negative 1 over k, then you have b. So putting a in first, b first, okay? Minus into bracket minus 1 over k over a. Okay, so at the end it's going to be a. So here is going to be what? Minus k over b plus k over a. Okay, so which is the same as this is the same as k over a minus k over b. Let's note this so that when you're writing it, you don't make a mistake. So this is going to be k over a, k over b, which is the same as k out, 1 over a minus 1 over b, which is also the same as, now let's put in place of k, which is 1 over 4 epsilon naught, okay, bracket 1 over a minus 1 over b. Right, so that will be the work done formula for moving a unit, a positively charged unit moment in the field of a positively charged body. Right, so if you get it well, so from here, just a brief over up to this point is b, and then from here to here is a. Okay, so as you are bringing the force, which is a positive unit charge, if you are bringing it, there's repulsion. Okay, that force starts from somewhere here in F, then comes to F final, F initial to F final. Okay, so it's more or less you have F against plotting F against distance, which is R. Okay, so this is the change in R and this F. So if you integrate F times change in R, okay, you get the work done over that distance. Okay, so you sum the various, you integrate F, the same as summing the F's. Okay, so the F's are there, you are summing them, you get the answer. Okay, you get the answer, the various. So F, as F is going, it's changing. So the various sums of F up to D should give you the answer. So that means because F is changing, okay, you can have those changes. Let's say this is coming that, okay, that is giving a picture of integration. So you can use the principle of integration to get the answer. So this is your F times this distance, which is the R, and then it gives you the work done. Okay, so you can look at it from that perspective. Okay, right. So it's always the force in play, force in position, the force in context, over the distance, the direction of the distance. Over the distance. The distance that is being moved is also in the direction of the force. Okay, then that is the work done. Right, so that is it. Okay. So let's look at this scenario and look at this. So if you look at this very well, you'll see that this comes up as the difference between the potential, this is the potential at A minus potential at B. So that is if you are moving from there towards the force. The potential here and the potential here, the difference is equal to the work done. So we could have straight away work it as the potential at A minus potential at B. Why not potential at B minus potential at A? This is work done. So work done is not a vector quantity, it's a scalar quantity. So you want the biggest, you subtract the smallest from the biggest, okay? And this reference of potential here is not as we have indicated in the other ones, okay? So this becomes just the voltage, the potential at A minus the potential at B, okay? Where B is positioned as a smaller, is further away, has lower potential, and this has a bigger potential. Alright, so this is in electrostatic field, okay? So with reference to a positive charge. So reference to a positive charge, this will be greater in terms of force here than the force here, okay? So closer to the body, the force is greater. So the direction, your field is the direction in which a positive charge will move, okay? So with a positive charge here, the force will be greater here than the force here, okay? And that is why, of course, you can just say that is why the difference here, in finding the difference, the potential here minus the potential here gives you the work done, right? Okay. So that would mean that is for work done, okay? But the potential at the place is by reference, and then we can look at it in that sense. All right. So let's play what we've done so far. So let's look at the next chapter. So let's briefly go over. Let's say it's a positive charge, and it has this distance A. This is a unit charge. This a distance at distance B from A, from this positive charge. Okay. Now we can move a positive charge closer to C. We can have these two at this point A, distance A. Then let's say we have another positive charge here. Then have this here positive. I'm just giving an illustration so that when we are looking through the questions, we can reason to this is A. Okay, this distance is B. This distance is B. Okay, so let's look at the three scenarios very well. Okay, so let's say we can ask you to find the work done. Work done as we move from here to this point by a positive, small positive, 1 unit charge positive. Okay, so in that case, it is the force times what the distance R. Okay, that is the work done. That will be the work done, and that you can use to work out. Or it also comes back to the differences in potential, the potential difference. Okay, the smallest and the biggest minus the smallest. So the biggest will be here. So VA minus VB. This is what I mean. Now, when you come here to, let's say we want to find the potential here, not work done. The potential here. We want the potential here. That is the strength here in terms of energy, the strength here, due to this and that. Okay, so in that case, the potential at A will be equal to what? The potential, this is contributing here. So we look at it here, the potential for this one, which is V, A, due to this one, due to charge, this charge, the first charge, the second charge, due to the first charge, plus the potential here due to the second charge. So this due to the second charge. Okay? So that will give you, so if let's say this is the charge here is 2 and this is 2, then of course whatever they contribute here is going to be times 2. Okay? That is it. Now if it is positive, if one is negative and this is positive, this will maintain the charge, the voltage that it will have given us A here, but this is going to be negative, so it's going to be minus what V A here, okay? Of course, this is a potential due to this one. Okay, so with reference, if the reference is to this point, if it is to this one, and the distance is being taken from this, okay, then you know, right? Okay, so if we are looking at the potential here, so it will be case minus that because this is going to make it going to negative. So let's say this minus plus 2 and this minus 2, then of course you see it to come out to 0. Okay. So if we are moving this positive charge here, we want to see the work done. Then the difference, of course, as this is coming, in terms of the force between the two, the force between the two, it will not be the same as if it is positive. Okay, so with reference to this one at the fixed point, then the force between the two will be generated as Q by Q. Okay, so that will be the force. Then you can sum that force over the distance. Okay, and then that will give it. Of course, it will become 1, it will be negative because of the presence of this negative sign. Right. So the third one, if we choose this as a reference point, okay, then of course, if this is VA, this is coming as being negative, okay, we stand there, but it will depend on the distance here. Of course, we are using this as reference, so the distance from this is just what we're going to use, okay, and that will give us the equation as that. Okay, so you have your VA minus your V, the same, that is V to the point B. So VB, okay, so this distance here and VB, okay, moving what we're looking at. Okay, so you can look at the VA potential here and the potential there. So this one is just looking at the potential. We are talking about potential, not the energy, so the potential. Okay, so in terms of energy, it will reflect the difference in potential will be the difference in potential will be the energy. Of course, in terms of difference, you are looking at the bigger from the smaller because it's a scalar kind of quantity. Right, that's what we are talking about. Okay, so I think at this point we can move on the electrostatic forces and go on to capacities, which will still have some part of electrostatic force. So the capacitor, this is our capacitor. Capacitor is something that charges, can store energy in a form of charge. So this is our battery here, okay, and then let's assume we have a resistor. So let's say we have a resistor here. Okay, so in actual sense, this is the battery as its MF. The battery has its EMF. Okay, now electrons will start moving. So when they come here, they are negative charge. Because they are negative charge, they are going to be this is going to be positive. Okay, right. But because there's an insulator here, it doesn't allow electricity to pass, electrons to pass through. So this is a capacitor. So the charge will build up. So when you close the circuit, so let's say this is a circuit, you close it. You close the circuit, okay? And the current will flow like that. So they will go onto this plate until they charge this one to nothing. So if you have a graph like that, it starts like that, it starts going up until it gets to nothing. Okay? And so it charges until everything here becomes the potential difference between across this one and across this one. Okay, that is our E. This is our E. Okay, that's the electromotive force. Okay, the force that is driving electrons in the battery or the cell. Okay, so that is it. It goes up to the 8th maximum point and then discharges. So when it does that, when it's fully charged, this is usually used in circuits or in gadgets. Okay, so at the point where the charge has been stored, the thing is not in use, then you have switched off. This can discharge, this can then become more or less like a battery and then discharge, carry on with other functions in the gadgets. Okay, that's the function of the insulator, the capacitor. Alright, so that is the principle here. So we can we have the graph here, we have that. So if you want to have an equation for it, then we can have what the simple equation as we know the what I call here, like you want to say cell. Here means the voltage is equal to the current times what resistance. This Ohm's law, okay? So that you say that voltage is proportional to the current that is flowing, okay? So voltage is proportional to the current flowing, okay? Right, and then voltage is also, so voltage is equal to your current times your resistance. All right. Okay, so let's look at another one, the definition, which is very important. Current is defined by definition is the rate of change of charge with respect to time. The rate of change of charge. So the rate of change of charge is current, or the Q, the T is current. So this definition is very important. You need it in a lot of equations. And then you have these two. So there's the Ohm's law, and there's the definition of current. Okay. So see that it is the movement of charges or the movement of electrons, which constitutes current. Okay, right. But by convention, we said if electrons are moving this way, current is moving that way. That is the current. This positive current is moving that way. Okay. So if it is positive charge, it gets here to give you a negative charge, then it causes it. Right. Okay, so the point has been made. So to remember cell there, so that will let you remember the formula very easily, and you are good to go. Right, so let's look at this the same capacitor, which is discharging to, let's say, after it has stored energy. Now it's going to discharge the current to this load. Okay, this can be anything to do with maybe a bulb here to light or something. So that's the load. The load is a bulb or any device in it. Okay, so this is flowing. Now we already have the formula V is equal to IR. Okay, so we can say I is equal to V over R. Of course, we said I is the same as the Q over dt is equal to V R. Then, in this case, this is our R, okay? In this case, we can have the Q is equal to V over R dt, okay? Right. So, this expression is what we want to look at definitely. If we can look at the other portions of the equation and then